Hello, students. Today we're going to be taking a look at section 14.2, and I'm also going to be addressing how I've updated a couple things. Not a lot, but if you can kind of take a look here, actually off to the left, I'll address it now. You can see that I've created a section on its own entitled Remote Calendar-Info. And that'll be an easier access point for us to then say, oh, here's the calendar. This is exactly and only where you'll find the calendar from now on. It's not going to be in just remote or in remote chapter 11, 14, and so on. So that's where I'm at now. So remote calendar-info section, and then the calendar looks just like as it has in the past. We are obviously looking at, like I said, 14-2. So let's jump in. So in section 14.2, we're going to be taking a look at tangents to a circle. What is a tangent? Well, a tangent is a line in the plane of a circle that intersects the circle in exactly one point. Three important theorems involving tangents are the following. In a plane, if a line is a tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. I'm going to draw a circle to highlight what this kind of looks like here. Let's draw our circle. And you can draw one as well. You don't have to be, of course, in line with what I'm doing exactly. I get to use the tools here for today. So again, in a plane, so a plane just means a two-dimensional surface, like our piece of paper here, or for me, my tablet surface. If a line is tangent to a circle, then it is perpendicular to the radius. So I'm going to go ahead and draw my radius of my circle. It's going to look like this. Okay, we're all familiar with that. I'm also going to put a point here on the circle. The tangent line, again, will touch the circle, and it'll look and affect something like this. I'm going to make it an official line with two arrows, in which, again, it's perpendicular to the radius. So here's my perpendicular relationship between the radius and the tangent. Second theorem, in a plane, if a line is perpendicular to a radius of a circle at its endpoint on the circle, then the line is tangent of the circle. So this is actually the converse of the first theorem. So the first theorem indicated that if you already know you have a tangent line, then it's perpendicular. You start with it being tangent, and then you end with it being perpendicular. Here, you're starting with it being perpendicular, and you're ending with it being tangent. Again, the converse simply flips the hypothesis and the conclusion. So really the same picture applies. The third theorem, if two segments from the same exterior point are tangent to a circle, then they are congruent. Let's draw this. Let's see here. There's our circle. Okay. So two segments from the same exterior point. I'm going to pick an exterior point, let's say here. Okay. So if we want to again draw or highlight our, let's say, radii, put a radius here. I'll put a radius there. In advance of really knowing how these tangents are going to look, I'm going to go ahead and put 2 points here and here. The tangents to each one of those respective points through the exterior point there in blue look something like this. Here's one tangent, and here's another. And actually, I'm going to make it a segment, pardon. Like and then another segment. Okay. The perpendicular relationship still applies for both of these. More specifically, because again, we have this situation where we've got the tangents basically having the same exterior point. I'm going to go ahead and highlight this segment. congruent to that segment. It actually does go back to congruent triangles, which I'll give you a little sneak peek on. If you were to then also connect the center to the tangent point, or exterior point, excuse me, creating the tangent lines, you have congruent triangles. They're both right triangles, technically. But the two blue lines is what we're shooting for as far as justifying the theorem. Example, find the value of x if AB is tangent to circle C. I'm going to draw in the picture a right angle because the radius of 8 and the tangent of AB form 90 degrees. Now they do say that here in the first sentence, which is great. Tangent AB is perpendicular to radius BC. Again, as I've noted earlier, the segment noted as 8 units. Also, AC is equal, so this whole segment is equal to AD plus BC, which is also what? Equal to 17. Now, the reason they can say that is because, well, the radius is 8, not just for segment BC, but for segment CD, this is 8. Therefore, you can add the 2 to get 17. Okay. So from there, we can apply the Pythagorean theorem pretty nicely. AB, which is a leg, x, squared plus BC squared. So AB squared plus BC squared is equal to the hypotenuse AC squared, which we know is, again, 17. Simply, again, A squared plus B squared equals C squared. Because it's a right triangle, we can justify it that way. X squared plus 8 squared equals 17 squared. Do the math. So 17 squared, subtract 8 squared, or 289 minus 64 ends up being 225. Square root both sides, and we'll end up with then 15 for the segment AB. Let's move on. So we've got a nice variety of questions here to take a look at. We'll jump in here. For each circle C, find the value of x. Assume segments that appear to be tangent are tangent. Okay, so if we take a look at our picture, we can see that we have circle C. We've also got an exterior point, which I'm going to highlight as such. Which takes us back to the third theorem up above, if you recall. Because we've got two tangent segments that intersect outside of the circle at this one specific blue point, we know that this segment and this segment are, because one is x, I'll label the other x. We also have this perpendicular relationship to take into account, which is quite nice in the sense that, well, we've got 90 degrees at this point. And 90 degrees at that point. We also have a 90-degree angle at point C, which is very nice because it justifies that, well, with this quadrilateral that's formed, we actually have one more right angle. It has to be a right angle because the four angles must add up to 360. So this angle right here is also 90. So what we observe here, quite nicely enough, is well, is a rectangle. So if we're going to apply the logic that we've kind of justified thus far, this would also have to be 19 technically, because it's a quadrilateral, more specifically a rectangle, even more specifically than that, because it's a rectangle, it's also a parallelogram. So this also must be 19, as must this. It's actually more specifically a square, not just a rectangle. Number 2. So if we look at again how we can kind of link the first theorem, we can say that that's 90 degrees due to the fact that we've got a tangent line. We've also got a radius of 15. We've got a hypotenuse, which I'm going to use in the context now of x. It's an unknown value, right? So we can use the Pythagorean theorem. So 15 squared plus 20 squared equals x squared. Now, if you recall, we back when we talked about the Pythagorean theorem, we talked about multiples of various right triangles. Nicely enough, being applicable. In this case, it applies very nice in context, where if you multiplied 345 times 5, you should end up getting 15, 20, and 25. So I am going to still use the calculator here, but technically what we should end up with x should just be 25. Because again, 345 times 5 is a 15, 20, 25. Let's double check. Okay, so as we continue, like I said, we'll double check on the calculator. So let's see, 15 squared plus 20 squared. That equals 625. If we take the square root of that number, we end up with, in fact, 25. Okay, number 3. So this one, again, is the third theorem up above, where because we know one of the tangent lines is 14 units, we also know that, well, because of those exterior or the exterior point being shared between the two tangents, we can also justify that the two segments there are congruent. Therefore, x is also 14. Okay, and if you wanted to justify why not with a little extra work here to show connection, go ahead and show your right angles as well with respect to the radii and the tangents. Okay, number 4. So similar situation as far as kind of what we're seeing on all questions actually thus far. So we have radii of 30. I'm going to fill that in. We've also got a tangent point. We've also got not exactly theorem 3 technically, but what we can do to justify which theorem in particular that we're going to utilize is we can drop down an altitude, but also remind ourselves that that's technically also a radius. We're actually creating two things. We're creating another radii or a radius of all the radii we can observe here. Of course, they're all 30. We've got our tangent points on the circle. Points of tangency are on the circle. And then we can justify, well, because we're trying to find x, remember that this will be the hypotenuse of any one of the two right triangles. If you want to look at it this way, this could also then be represented as x, because the two right triangles technically are in fact congruent. So we've got leg squared, so a squared plus leg squared, and that should equal the hypotenuse squared, called hypotenuse c in this case. Okay, and I'll label it. Now this actually ends up being very much more, I would say, easily relatable to a 3, 4, 5 in that it is a multiple of a 3, 4, 5 simply by 10. So this is a 30, 40, 50 right triangle. So nicely enough, we could argue then that that's 50, the hypotenuse. Because we're asked to find x, not c, we'll do the math and finish up in such a way where we'll subtract 50 minus the radius of 30. So 50 minus 30. And of course, that's number 5. Again, we've got ourselves a situation where we've got a tangent line to the circle at this point. This is the right angle that we can create out of that. We're asked to find x. Keep in mind, this is a radius of 21, but so is that. So in full, this hypotenuse, and I can easily argue that as the hypotenuse of this right triangle is simply 21 plus 8, which is 29. So I've got a squared plus b squared equals c squared. Let's double check, or at least see on the calculator how this can play out. 29 squared minus 21 squared. And that ends up being 400, the square root of which does end up as 20, a nice value. X is 20. Number 6, this one I'm going to leave for you to try on your own. It's a little bit of an extra challenge question. I will post the answer to your notes for today.